Okay, the point of this video is to describe what a rate law is, to look at what it looks like and make sure we understand what the terms are, and also to figure out how to use the method of initial rates, which is an experimental method. Well, not exactly experimental, but it's a method of setting up an experiment and then using the data from that experiment to determine a rate law. So first off, a rate law is a mathematical expression that shows how the rate depends on the concentration of the reactants. A synonym for rate law in this case is a differential rate law. In our next video, we'll discuss integrated rate laws, but for right now, rate law means differential rate law. And this rate law is always going to be determined experimentally. However, it can be predicted using theory and something called a mechanism, which is much later in the chapter, so don't worry about it right now. When we are looking at rate laws, we're always going to be looking only at the concentration of the reactants and their effect on the rate. And to do that effectively, we always need to be looking at kind of the initial rate. Hopefully you remember from today in class the instantaneous and average. Actually, an initial average rate would work here too, but hopefully you remember average and instantaneous rates and how I would get those from looking at a graph that plotted concentration versus time. If you do not, check your notes from today. Okay, so why is it important, before we get into what a rate law looks like and what it means, why is it important that we are measuring the rate at the beginning of the concentration, the initial rate? The answer for this is that almost all reactions, like this one, will establish an equilibrium. So in addition to having a forward reaction, so if we're measuring the rate of the forward reaction, or at least I hope in most cases that's what we're trying to measure. We'll want to measure at the very beginning when we only have NO2 present in the container. As it starts to convert to NO and O2, that will be mediated by the kinetics of this first reaction. So the forward reaction will determine how fast it's producing NO and O2. However, already in section B over here, what we might end up seeing is a reverse reaction where three molecules, although kind of rare, but where two NO molecules and one O2 molecule may actually collide to go back to 2 NO2. So if I'm measuring the concentration of NO2, the change in concentration of NO2 over time, what I may end up seeing is that some NO2 is being converted, and that's what I think I'm measuring. I'm measuring the rate at which NO2 is disappearing. But at the same time, there should be some backwards reaction after the first moments of the reaction. And so the concentration of NO2 is also influenced by the rate of the backwards reaction, right? Some of it will be being formed again. Which is why we always want to measure the initial rate to determine the differential rate law. So what is a rate law? Well, for this general reaction, A plus B goes to C plus D, the rate law is going to look like this. Rate equals K, square brackets A raised to the N, square brackets B raised to the M. The various parts of this the various parts of this equation hopefully are fairly self-explanatory. We talked about rate in class. It's always going to have some sort of look like that. It's important, however, when you're setting up an experiment, measuring a rate, whatever, to define whether you're talking about the rate of change of A or the rate of change of B, etc. All right, little k, this is important. It's not a big K here. Little k is called the rate constant, and it's dependent on the temperature, on the reaction itself. So what I mean when I say that is that, if I reacted A plus B plus Z to get C and D, that rate constant that I would have got here for A plus B goes to C plus D would not apply. And that's it. So square brackets A and B are the concentrations of the reactants. You see that the concentration of the products is not included here. And finally, N is the order of the reaction with respect to A. M, similarly, is the order of the reaction with respect to B. And both of those coefficients, or sorry, they're not coefficients. Please do not think that they're coefficients. Those powers show how the rate law is mediated, or sorry, how the rate is dependent on the concentration of A and B, respectively. If I sum them up, and if I had like 5 reactants and I had, NM, OP, whatever, I would sum up all of them. The sum of all of those is called the order of the reaction. Okay, so how do I determine all of this stuff experimentally, and how do I do the math, essentially? So how do I experimentally determine a rate law? I use what's called the method of initial rates. This is going to be a series of experiments that you set up in which you vary the concentration of one reactant while holding the others constant. And then vice versa. What I mean is then you would hold that one constant while changing up the other ones. And observe the effect on rate. Okay. The kind of data that you get then looks like this data over here, right? We have nitrogen dioxide, carbon monoxide reacting according to this equation down here. You can see I start with initial concentrations. So that's important, right? Method of initial rates. We're also going to be looking at what are called initial concentrations, which sometimes are designated with that little O down there. So anyway, the initial concentration of nitrogen dioxide and of carbon monoxide give this rate. When I double the amount of NO2 and keep CO the same, I get this rate, and so on and so forth. So how am I going to determine the order of both reactants, right? So I'm looking for N and M in the equation rate. This is going to be the generic rate law, right? Rate equals K, NO2, N, CO, M, and the value of the rate constant and the rate law. Okay, so I'm going to be looking for the orders of both reactants. Once I get the order of both reactants, I can solve for a value of the rate constant by using the data that I'm provided just in one of the rows there. And the rate law will be just that written out again, but now with a value in for K and N and M with actual numbers in them. So how am I going to do this? Well, we've got my series of experiments. I want to see how changing each, this is what you're going to be looking for. How does changing concentration of one reactant affect rate? So in these cases, I'm going to be looking at ratios. So for example, in experiment 1 and 2, right, the first two, I see that NO2 is doubled as you go from 2 to 1. So I like whole numbers instead of fractions. So let's see. If I change the concentration of NO2 from 0.1 to 0.2, that means I've doubled the concentration. What happens to the rate? The rate quadruples, okay, roughly. Okay, what does that mean? Well, all of these can be put into, remember, the concentration of the thing is going to be, of the reactant is going to be raised to a power. So really what I'm seeing here is that when I raise this concentration change to some power n, right, I see a change of 4 in the product, or I'm sorry, in the rate. Okay, so solving for n here, we know that n equals 2. That means the order of the reaction with respect to NO2 is 2. So now we got to look at the effect of changing carbon monoxide while nitrogen dioxide is held similar. So now I'm going to look at experiment, I'm going to look at experiment 2 and 3. And I see that when I double the concentration of carbon monoxide holding nitrogen dioxide steady, I actually see this, right? I see that there's no dependence of the concentration of, no dependence of the rate on the concentration of carbon monoxide. That means M equals 0. Right, so our rate law so far, and how we're going to solve for K, move this up a little bit, is going to be equal to K NO2 squared. And I'm going to leave CO out, because when you raise CO to the 0, you get 1. So now I want to solve for K. I'm going to do that by just choosing an experiment. Let's look at experiment 1. The rate was 0.0021. I do want to use the units, because the units are important. And that's going to equal K times NO2 squared. The concentration of NO2 in this case is 0.10 molar squared. Right, kind of coming over here, I have 0.0021 molar over seconds divided by, this is very sad, by 0.01 molar squared. Remember, if this squared applies to the unit as well as the value, equals K. I can get a value now, but I can also get the units. If you look at the units, here one of the molarities is going to cancel out with that molarity up there, and we're going to end up getting 0.21, and our units are going to be molarity to the -1, right, because it's 1 over molarity times seconds also in the bottom, and that's going to be my value of K. The units of K are different for different reactions, different kind of experimental methods, and so on and so forth. So it's always important that you pay attention to the units of K. They will not be the same. Last but not least, what is our rate law? I'm just going to write it up here. Our rate law is rate equals 0.21, molarity -1, seconds -1, times NO2 squared.